second lecture of EE40. Last time I hope that I managed to convince you that electronics is a really cool thing. You can do a lot of things, and of course the most fun part of it is to be creative, to do new things, to invent new things, and then realize them and see them out in the world. That's always rewarding. But in order to do that, we of course need to figure out how to design them. We need to figure out how they work and so on. So let's get started on that. So what makes an electronic circuit tick? Well, here is an example, an Intel, some kind of an Intel processor, a more recent one, over 1 billion transistors. It has six cores. What are all these transistors doing in there? Okay, so question, right? Well, here is another example, a circuit. So actually, maybe I should say a few more words on this one. So one way we can understand the circuits like this one working, they send electrons around, they push electrons from one transistor to the next one and so on, and that's how they're working. So it's kind of sort of almost a little bit of a mechanistic model. But that's not always so, right? We also know that electronics, of course, can work wireless. It can work through all sorts of things. And so here is an example where, for example, just the presence of our hand can change the way electronics operates. So all of it means that it can be pretty complicated what's going on. And of course, we can ask physics, and physics gives us explanations on what's actually going on. Physics tells us, well, what really happens in electronics is that there are charges, usually electrons, could be also other charges, and there are fields, and through these fields they interact with each other. And so these processes, they're fairly complex. We said that already. We said also, just in the title, that physics uses models of charges and electromagnetic fields to explain what's going on. And mathematically even, these concepts, they're captured very well in something called Maxwell's equations. And they're very accurate. They really capture all that's going on. For example, if you wanted to know, or if you had analyzed that iPhone there with Maxwell's equation, you had included the model of had included the hand, and so you certainly would have found out that the presence of the hand will modulate the receive or transmit strength. But again, the disadvantage of this accuracy, of course, is that it's extremely complex and extremely tedious. We would not get very far at all. We wouldn't design just about anything at all if we were to use Maxwell's equations here in EE40. So if I scared you, don't be scared. So in practice, we'll have to use approximations. And approximations, of course, is a very mixed bag. Right? On one hand, it does what we want to accomplish here. It removes much of the complexity that, in this case, really gets in the way of designing interesting circuits. But on the other hand, approximations, well, they're not always true, right? And we have to pick the right ones, and sometimes we violate them, and then we may fall on our nose, or we will get something that doesn't behave the way we think it should. So we'll have to talk a little bit about the approximations that we are going to use in EE40. Note also that this is very different from other classes you've been taking. If you take a CS class, well, a computer is really a concept. It uses Boolean algebra and so on. Almost a mathematical concept that's created by man when we program computers. So then we are not really a subject anymore. Mostly physics is abstracted away, right? And we have a sort of an ideal world, at least in the sense that things behave exactly the way we describe them according to some mathematical formalism. Obviously, in math, that's always true, right? We can write any kind of equations, and these equations have one solution, and that one is the correct one, and all other solutions are wrong. The minute we get to physical systems, and in EE40 we'll have to deal with physical systems, things are no longer so simple, right? The reality is exceedingly complicated. We can't really deal with that reality in any practical way. People would never have designed any circuit of any interest if they were bent on describing it accurately. we'll have to use these approximations. And approximations, of course, they depend on the application. If you build a radio, you have to use different applications than if you build a computer. All right, so just sort of for a joke, in case you wondered, these are Maxwell's equations. You can download them from the web, or maybe who heard about them in physics, in a physics class? Oh, okay, well, so you know all about it, right? So they tell you what's going on. They tell you about, they link charge densities to fields and so on. But we're not going to use these Maxwell's equations here. So what instead we are going to use is usually referred to as a lumped circuit approximation. So the lumped circuit approximations make one huge assumption that is sometimes true and sometimes not. Actually, it's never quite true, but it's often sufficiently true that we can use it practically. So what is this assumption? Well, it means the assumption is that there is no interaction at distance. What do I mean? Well, that components only react with each other or interact with each other through wires. Okay? They don't interact each other through an electromagnetic field or so that goes through the air. Okay? Or doesn't need wires or so. Okay? So the advantage of this assumption is very profound, because now we can think of a circuit as being a bunch of components and then wires that connect them with each other. Note that's not at all true what's really happening. Right? In reality, there is an electromagnetic field that goes everywhere, and it doesn't really care about the wires. Well, it does care about the wires, but it's not bound by these wires. But if we make the assumption that we don't have interaction at a distance, then we can think about circuits as just components and wires that connect them to each other. In fact, we can then use an analogy. A circuit then behaves very similar to pipes that correspond to the wires and would carry not water but electrons in the case of the electronic circuit. And water in pipes, and then there would be components like pumps and valves and so on that regulate the water flow. Well, in electronics, those are going to be batteries and transistors and other resistors and so on. Okay, so now obviously, and I mentioned that already, the minute we make assumption, we got to be very, very careful because assumptions are not always true, right? These particular assumptions that we are using here, no interaction at the distance, except through long wires, perhaps. That works usually for computer chips, but even there, it works only, and we'll see why shortly, it works only if they are not too big, these computer chips, and they don't go too fast. Okay? We'll see why that is in just a moment. So it doesn't obviously work for RF, it doesn't work for antennas, right? Because there are no wires, but signals actually get transmitted. Isn't it incredible, right? If there is a radio station somewhere in Europe and you listen to it here, what actually happens is that electrons get pushed around in Europe, and then here in your circuit, electrons get again pushed around at that distance. But anyways, we're not going to study that here, but that's what's happening, right? So we have to know what our assumptions are. So let's list formally the assumptions that we're going to use in 4D. Okay, so there are really just three assumptions that we are making. The first assumption is that the electrical interactions between components, that they happen instantaneously. Okay, so that signals, current or voltage or whatever, propagates on wires instantaneously. Okay? We'll talk about each of these assumptions in just a moment. Right now, I'll just list them. Okay? Incidentally, I see many of you taking notes. That's good. If you can also download these slides from the web if you prefer, and I try to upload them always before the class, and then you can mark up the slides if you like that. I think you had a question? Okay. Yeah. All right. So, Okay, so the second assumption we already said, sort of that's the key assumption, right, that we really are going to use all over, that electrical components interact solely through wires. And then the third one is almost always met, but for completeness we have to add it here also, and that is that the net charge on electrical components is always zero. We'll talk about that in detail, each of them now, okay? But these are the assumptions, so if ever you wonder, well, something's not happening the way I think it's happening in my circuit, what could it be? Well, then you can go back to these assumptions and check each of them. So the first one is this instantaneous interaction. So we've already said what it really is. So for example, if we plug an extension cord into one of these outlets, and then we look at the other side of the extension cord, of course we get 110 volts there too, right? We have it 110 volts in the plug. We plug in the extension cord, and then we better don't have our hand on the other side of that extension cord because we're going to have 110 volts there. But is that going to be instantaneous? If we were really fast with our hands, could we plug it in, have our hand on the other side of the extension cord, somehow stick it into the prongs? You need to have small fingers, right? And touch it, and then let go just before the high voltage arrives. Would that work? Why not? Okay, we are too slow, right? We are too slow. But if we were really, really, really fast, would it work? No. Okay, fine. Really. So that's what the answer is. There is the speed of light. If we can be as fast, or maybe a little bit, just a tad bit faster than the speed of light, then maybe, in fact, it's going to be a little bit less actually than the speed of light, but very close, right? Within a factor of 2 or less than 2 in this case. That the signal propagates down to the other side. So it's not instantaneous, right? Electrical signals, they go very, very fast. Speed of light's pretty fast. Actually, anybody remembers? 300,000 kilometers per second, right? Yes. So actually, there is I like to convert that. It goes 30 centimeters in 1 nanosecond. Okay, so why is that more useful? Well, 30 centimeters, heck, I can think of, well, that's about 30 centimeters. Okay, so that part is good. Now, the nanoseconds are a little bit harder, right? The nanoseconds is a little bit harder, but who has a computer here? Well, you all have computers. How fast does it go? About a gigahertz. Let's pick a gigahertz as a simple number. Okay, round number. So 1 gigahertz, that means that it performs 1 giga or 1 billion operations per second, right? So how much time does it take just for one operation? 1 nanosecond, right? 1 second divided by a billion, that's a 1 billionth of a second, and 1 billionth, that's nano, so 1 nanosecond. In 1 nanosecond, the computer does 1 operation, okay? So, and in that 1 nanosecond, light, or for that matter, an electrical signal, managed to go how far? Well, 30 centimeters, about that long, or a foot if you're like the American or English notation. Okay, so that's how far it goes. So, hey, you know, the speed of light is fast, but if you think about electronics, it's not that terribly fast after all, right? Now, how big is your computer? Well, it is about 30 centimeters, right? So in the time of the computer makes 1 operation, a beam of light could just go from one end to the other end of your laptop computer, right? Now, why does it work? Why can your computer go that fast at the gigahertz, where light couldn't even, or just barely could travel from one side to the other, and again, an electrical signal. Yeah.
The component doing whatever operation is very small.
Right, exactly. Exactly. The component that does the operation, the CPU, this computer chip, that thing that we looked at, the pretty picture at before, maybe a centimeter on a side. If it's a really big one, maybe 1.5 centimeters on a side. And moreover, inside the port that actually does the addition or multiplication or so that happens that fast is even smaller, that may be 100 micron on the side. Okay? So just a tenth of a millimeter or so on the side. So the reason it works is that things are pretty small, right? And so actually, you may remember on one of my earlier slides I said, you know, even for computers our application or assumption applies only if they're not too fast, not too big. Well, that's what I meant, right? If our computer chip really was as big as an entire laptop, 30 centimeters on the side, well, we would have mighty problems there. Okay? And likewise, if you make a computer go at 10 gigahertz, how far does an electrical signal travel, assuming that it goes at the speed of light? Just 3 centimeters, right? So then now it's getting pretty close to the size of a computer chip. Okay? So okay. So it's an assumption that we can check. Usually it's met. Why is it usually met in? Why is actually we'll stick with this one? Why is this assumption of instantaneous interaction usually met in EE40 circuits? Any guess?
Because we're not working with signals that vary really quickly.
So now we need to make sure that others get involved too. Yeah, exactly. We usually, in EE40, we don't build anything that goes near the speed of 1 gigahertz. Maybe 1 megahertz, that's about the max. Because otherwise, this breadboard, this white stuff that we use in the laboratory, all of that starts acting like one big, complicated, messy antenna, and the signals don't behave at all the way we would like them to behave. Okay, so in EE40, we stick to speeds or clock rates, megahertz and less, and then instantaneous is pretty good, right? At 1 megahertz, right? On 1 gigahertz, 1 gigahertz light travels 30 centimeters at 1 nanosecond. In 1 microsecond, which is 1 over a megahertz, right? How far does light go? Well, 30,000 centimeters. I'll let you convert that to meters. It's still not such an incredibly long distance, right? It's a distance that you certainly, well, it's further from your home or from your dorm to school, but nevertheless, I mean, in 1 microsecond, it took you longer to get here, right? Okay, so in EE40, the assumption is usually made simply because even though our circuits sometimes are pretty big, and they may be actually 30 centimeters on a side, just because we don't miniaturize things, right? It's easier to build in the lab if we have a little bit of space. We don't go that terribly fast, okay? So that's why it's okay in EE40. And also, it's okay in that computer chip because that thing, even though it has 1 billion components, is so small that it's almost instantaneous, okay? So here, now the second assumption was interact through wires. So that's a wonderful thing. The minute we can say that the circuits, they only interact through wires, we can draw something like here that's called a circuit diagram, where we have the blue things, and we'll talk about those, of course, in much more detail. The blue things, there's a circuit components. There could be batteries, resistors, capacitors, could be entire computer chips, right? And then there's the green stuff. Those are the wires, and they really make a circuit out of it. They make it that now the different pieces can talk to each other and start doing useful things. Okay, that would not be possible if we didn't have this. If we didn't make this assumption, for example, in a radio, that obviously is not true, right? Because signals they propagate, the blue components they interact with each other in antennas, even though there is no wire in between. That's the whole point of a wireless circuit. Okay, actually, so I need to, so let me, so it's a schematic. The schematic circuit that I've drawn at the left side, which is going to be, maybe look a little bit complicated right now, but this is going to help us all throughout EE40 and all through our electronic circuit design careers. These schematics, they work only if we can make the assumption that the circuits, the blue things, they operate through wires, the green things in this example here. So but then we got to be careful because when we have an antenna, we said already that's not the case. Well, okay, and then let me give me actually what's actually an antenna? It's a piece of wire, right? And it turns out the piece of wire to become an antenna, there's really one condition. And that is that the wavelengths and the length of the wire are sort of comparable, okay? So that, in other words, what's the wavelength? Well, it's basically the distance that light travels in one cycle of the frequency, so of the frequency that we are going. So again, at 1 gigahertz, the wavelength is actually 30 centimeters. It's the distance that the light travels in one cycle, in 1 nanosecond, okay, of the frequency at which the thing operates. And so, for sufficient size or sufficiently high speed, any wire becomes an antenna. Okay. So, for example, when you go to the lab, you will have an instrument that's called an oscilloscope. Sort of like a TV, but it doesn't show you soap operas. It shows you electrical signals inside a circuit, okay? And so if you use that instrument, just turn it on and you don't connect anything to it, or maybe just a probe to it, and then you will see actually a sine wave, usually. Why do you see a sine wave? Or at least if you touch it or so. Sometimes you will have to touch it or have to attach a wire to it or so, an antenna, right? You could be the antenna, a wire could be the antenna. And then you start seeing a sinusoid. Where in the world does this sinusoid come from? Yeah. Exactly. If you go to Europe, it's going to be 50 hertz, but here it's going to be 60 hertz, right? And so, of course, there are wires all over here, and they're pretty long and so on, and they act as antennas, and you touching that scope or whatever the probe touching the scope acts as a wire, as an antenna also, and so you're going to capture. You make actually a radio out of your scope, and it captures the 60 hertz. Okay, so even in EE40, and even though we go pretty slow and 60 hertz isn't very fast, right, then we still can see this effect. But fortunately, for all the things that we do, usually these effects are not going to be very significant. If you connect the scope to actually a wire in your circuit, it's not going to show you that 60 hertz is going to show you the signal at that point in the circuit. And there is also going to be just a little bit of 60 hertz on top of it, but why don't we care? It's still there. It's so terribly small that, you know, if it's 1 million or 10 million times smaller or so than our signal, we probably don't need to care. Okay? So the last assumption here, net charge is always 0. So we more or less said already that components, they interact through the wires, and they actually send electrons through these wires. Now, if you have a circuit component, that could be made out of anything, right? Then, of course, loss is made out of atoms, right? Atoms are going to be positive and negative charges. Negative charges on the electrons. So if electrons go away, well, then afterwards there's going to be more protons, more positive charges left. And then there are negative charges, and the component is net charged. Okay, so what happens then when a component has a net charge? Well, it immediately goes and attracts another charge in order to get neutralized again. And actually, that generally happens very, very quickly, and also generally has to happen. One of the reasons why it has to happen is that the forces, these electrostatic forces, get rather quickly very significant. And you see one effect of electrostatic force. If we manage to charge ourselves, right? This guy somehow got charged, maybe. Then all of our hairs start standing up because they actually repel each other because they're electrically charged, and all of them have the same charge. Right? What would happen if you were to strip all the electrons out of the poor little guy? Yeah, you would fall apart. But anyways, you could calculate the forces that this would generate, and it turns out that you could now use him to lift the entire Earth. I don't know how to do it. But in the homework, you're going to make a little calculation, and for even a smaller thing, you calculate that how many trucks you could lift if you could remove all the electrons from some kind of component. Now, these forces get very large. So in practice, except for exceedingly small times, that's usually always true, that the net charge is zero, and if we have wires also. Okay? So in the EE40, we're going to use a circuit model that is based on 3 assumptions. We've talked about them. And, of course, these assumptions are not always met. Usually in EE40 they are met, but if you have a doubt, then what are you going to do? Yeah, you will check them, right? And if they are not met, what are you going to do? Yeah, that's it. You use another theory, right? For example, you could go back to Maxwell's equation, or there are, of course, all sorts of other theories that are also simplifications of actually what's going on, but they simplify in some other way, and then they apply to other situations, like in EE 117 or so. You would look at different models like transmission lines or so that capture now the fact that signals, they don't go infinitely fast. Okay, so I'm becoming a little bit repetitive here. This thing is called lumped circuits, right? Because now, once we have this assumption, we really can divide the world up nicely into circuit components and then wires in between them. And I've already mentioned then we can use schematic diagrams. I just pulled this off the web, totally random schematic diagram. Don't care what it actually does. But the thing is that usually, the ones that I draw in the course, I'm always careful. I draw all my components blue, and I draw always the wires in green. And I find that sometimes that's helpful, because then we see right away, well, this is a component, it's blue, and this is a wire, it's green. But most people, they are not so careful. They simply draw everything in black. And so then we have to realize, well, this is a component. This hash thing, there is also a component in between. You have wires. But so one thing that's very convenient about these circuit diagrams is that it abstracts from a lot of things. Right? If you think about an electronic circuit, there's a lot that goes into it. Right? There is sort of the user experience. There is a case. There is a color. There is a particular shape, and so they're all very important, right? If this looks like a clunker, then, well, maybe nobody will buy it. And if it looks attractive, maybe this is attractive, then people will go for it. But when we just focus, when we just want to know, well, does it actually perform the function that it's supposed to do, then we really couldn't be bothered with whether it's green or red or blue or so, and we wouldn't want to have a fight over that. We need to determine why the signals that come out the other end are and what they're supposed to be. Right? So we can abstract from all of these shape, color, things like that with the circuit diagram. All we have are the components, and we somehow string them together. Where exactly, how we wire them and so on. There are neat ways to draw a circuit diagram. For example, that we have a few wires that cross each other and it gets ambiguous. Do they now make contact or not? You can use dots and so on to indicate that. But in principle, we could rearrange these components in any arbitrary fashion, and the wires will look like a terrible spaghetti, and it still will describe exactly the same circuit. And then so that circuit, and these are not all the same ones. You could also, when you go into the lab, well, then you actually have to take the components, you have to use wires, don't make such spaghetti as here. Why not? Yeah, it will still work if you do everything right, but probably you do something a little bit wrong, and then if you get in here, we want to probe or check something. Well, then you probably pull out one of the wires and wait, where did that one now go? So neatness really matters. You're going to build stuff like that, maybe not quite as complicated, and hopefully not as messy as this. So then once you prototyped everything and you found that it's actually working and it's doing pretty much what you want, then of course you build a more professional kind of thing. You probably a printed circuit board where you solder the components, and finally it may look something like this you put up. Okay. Oh, Laplace, the Maxwell equations, typo. Okay, so electronic circuits, really the physics is captured by Maxwell's equations, but they are accurate. They really is the true thing. They capture the true thing, but they make it too complicated to design any practical circuit. So then we use lumped circuits. We have a number of assumptions, and thanks to these assumptions, we can use schematic diagrams. All right. Are there questions? Good. So, stupid. Oh. Okay. Fine. So now we get on to the next topic, circuit diagrams. The actual lectures and the lecture notes, they're out of sync because sometimes the class is on 2 days and sometimes on 3 days, and so we sort of have lectures for 2 days when we actually have 3-day schedule here. All right, so schematic diagrams, you've seen this already. And we've said before, the blue stuff. And again, blue really is totally irrelevant. I just do this hoping not to confuse you, to help you a little bit. So I draw all the components in blue. Components are often also called branches. And here, for example, we would have how many branches in this circuit? Just count the components, so that would be 4. And then there is the connections, wires, who are also nodes, sometimes called nodes. Why? Well, because really we don't care at all. The physical extent of the wire is only because we couldn't draw it otherwise easily, right? How many nodes do we have here? Okay, 3. So now I could, of course, go and add a component now. Now I'm going to be lazy. And I'm just going to use black. Did I add wires? Yeah, I added wires. I added also a component. Now, of course, we have 5 components, right? And how many nodes do we have? Still 3. The number of components and the number of nodes has nothing to do with one another. Also, note that the number of dots and the number of nodes have nothing to do with each other. A dot is just for convenience. It's just to make sure that it's totally clear to everyone that this wire, and this wire, they're actually connected here together. That's particularly useful if we had yet another component. I drew this not very nicely now, right? Then this dot here at the top, of course, is needed to make it clear that all 4 wires there are connected. But on the left side there, where I made that little loop, sometimes we make this loop, sometimes we don't make the loop. Even if the loop isn't there, if there is no dot, the wires are not connected. Okay? So that's just nomenclature. And of course, again, it would have been much better if I had drawn this. If I had drawn this extra component just like this. because then I don't have this crossing and nothing that is not quite clear. And then, again, just to be safe, I always put the dots down. Okay? Comments? Questions? Okay, so that's quite straightforward. All right, then of course, what's going on here? Well, we will need to, at some point, get to current and voltage. You probably have heard about those. Well, at least you have heard about 110 volts. That's not so good, right, if you touch it at least. So what's current? Well, current is really just charge that moves around, and it's the amount of charge that moves per time. That's what current is. So what is charge? Well, again, for example, electrons, it's measured in Coulomb. That's the unit. And then the voltage. Voltage is sometimes called electromotive force. And the reason it's called that way is that voltage is really the thing that makes charges move around. Just like if we had actually, if this was actually a pneumatic model, right, then in the green stuff, there would be pipes, and we would not have electrons flowing there. We would have water flowing there. And what would make the water flow around in these pipes? A pump, right? So the voltage or the battery really corresponds to a pump in a pneumatic system. And the current, well, it corresponds to water flow. Okay? All right. Okay, so we would have, for example, well, we can now indicate the current. Let me put this here. So, for example, we could have here a current. We could call this current, for example, I1. We could also have a current here. That would be current I2. We could even have a current I3 here. Would I3 be equal to I1? Well, probably not, right? It would have the opposite sign. But it really, if I1, for example, was 1 ampere, then I3 would be simply minus 1 ampere. So the way we draw our arrows is totally irrelevant. Afterwards, if we drew the arrow the wrong way around, and there is really no wrong way around, well, just we get either a positive or a negative current, right, if we somehow were to measure it. But I4, would I4 be equal to I2? No, right? Because there may be current flowing here, I5, and if that one's not 0, well, then I2 and I4 would not be equal. Just like water, obviously, if we had a lot of water flowing there in I5, well, that water would have to come from I4 and would not be available for I2. We'll capture this more formally in just a moment. Okay? So far, just for currents, we use these arrows and we give them names. And, well, we could also just call it some other thing like Fred. Whatever. Pick your names. The longer the nicer, but maybe it gets a little bit tedious to write them and get confusing because of that. Okay, so then we also can have voltages, and those we indicate with pluses and minuses. For example, here we could, again, let me call VA, just any kind of a name. We also could have a voltage here. This is not very good. Maybe I should. Where do I have my eraser? Oh well. Here, this is the eraser that. So here we could also have VB, okay, right? And so actually, would VA and VB be equal? Yes, they actually would be equal. And again, we'll look at that more formally in a moment, but because they're on the same wire, the pluses and the minuses, well, then they're going to be equal. Like I can play again the same trick here. I can put the plus and the minus on opposite side, and then we see that would actually be minus VA or minus VB. Okay? What about What about VD? Well, that's 0, right? Because we actually said that the signals, they move in wires. Okay. All right, let's look just a little bit more at current. So we've said current, really what it is, it's like water flowing in pipes. Well, here it's electrons, charge, coulombs, that flow in wires. Now, most of the time in the electronic systems that we build, the charges are actually electrons. There are other electronic systems, like our nervous system or so, that sometimes uses charges too. It doesn't use electrons, it uses what? Ions, right? Which, of course, if you take them apart, there are also electrons inside, but one of the interesting things is that with ions, you can have actually larger charge. Larger than 1.6 times 10 to the minus 19, so a very small number coulombs. That's the charge that you get from an electron. So that means also because the charges, electrons are such a small charge, there are lots of electrons in a coulomb, namely 6 times 10 to the 18th electrons per coulomb. So we will just get to in a moment to what that could mean, how we could imagine that. So if we then take a conductor, for example, copper is a good conductor, like many metals, and copper is particularly good. Then, of course, inside the copper, there are copper atoms, they have protons, and they have electrons around them, but the important thing in a conductor is that some of the electrons in the outer shells of the atom, they're not stuck very strongly to the atom, they're free to move around. And that really makes it a conductor. And so we could then ask the question, well, how many of these free electrons do we have in a piece of copper? And the answer is approximately, depends on temperature and so on, but it's approximately 10 to the 24th electrons per cubic centimeter. Okay? That's how many electrons are available per cubic centimeter in copper. So now let's ask ourselves the question. Let's say that we have here a piece of wire that I drew here, this blue thing. Okay, so this is a wire. It's round. It has a cross section of 1 millimeter square. Let's ask ourselves the question: how big a piece of wire do we need that we have 1 coulomb worth of electrons that can move around freely? So we calculate this length L here that we need, and then in this segment, the darkish blue segment of the wire, all these electrons in there, they make up a coulomb, and these are the electrons that actually could move around if we had a current flowing. Okay? And so, of course, we can use the density of electrons. I think you can calculate it yourselves. We can use the cross-section and then divide, and we get and we also have to use the coulomb, and we get that in a section of only just 6 micron length of that wire, we have here 1 coulomb, or 6 times 10 to the 18th electrons. Okay, just in this segment of wire, 6 microns long, we have a full coulomb of electrons. So we could actually calculate it. Why don't we do this quickly? So this length L is equal to, first of all, the charge that we have here. That's 1 coulomb. Okay? And then we have to divide by the charge density. That's this N copper. Okay? That's this number here. And then we also have to multiply by the charge, of course, and then by the cross-section. Okay? That's how we get that length. Well, we could have multiplied, then we really get the total number of electrons. L times the denominator is the total number, the total charge in the volume L times A. Okay? So now let's ask ourselves another question. Let's suppose that now actually a current was flowing in this wire. Okay? Let's say the current was just 1 amp large. And so now the question, not from you, the answer. Okay? The question is, there is 1 amp, I can even show it, mark it, right? There is a 1 amp current flowing here. How fast how fast do the electrons move in this wire? Yeah. But didn't we, so 6 microns per second, is that fast? We can go faster, right? I mean, if you had come at 6 microns per second from your dorm here, you would have missed class, right? But didn't we say that electrical signals go at the speed of light? Yeah. Well, yeah.
So maybe the electric field travels at the speed of light, and then once that is established, all the electrons move at the same time.
Okay, yeah, that's right. Yeah.
Like water in a pipe, you don't have to wait 5 minutes after opening a faucet for water to come out.
That's a good analogy.
It just needs a chance to move.
Right, that's a good analogy. Yeah.
Because they're very fast together, so if the first one moves, the last one moves.
Yeah.
This is the drifting speed. Actually, all the electrons are going in all the directions. They're going at the speed of light. But right now, this speed right here is just they're bumping each other to move in the direction of the wire.
Yeah. Okay. So whether the electrons go at the speed of light or not, not so sure. But anyways, I think we pretty much have the explanation, right? The electrons, yes, they do go only very, very, very slowly. But just like in the faucet, right, the water doesn't have to go all the way from the reservoir when you open the faucet. Well, water is already in the pipes. If we were to empty the pipes every time totally of water and the wires every time totally of electrons, we couldn't do that, right? We could do it with the pipes, but not with the wires. Then we would indeed have to wait exceedingly long, okay? So electrons actually, I find that just interesting. Electrons move very, very slowly. But electrical signals, they travel fast. And yes, we can use the electrical field as a, that really tells us how fast things are going. That the electrical field goes at the speed of light or very close to it. Depends. If it's in vacuum, it goes at the speed of light. If it's in a material, then it goes a little bit slower. Yes. Okay. So the question is whether whether I put this on BSpace or on the course web. Yes, usually I will do that. Usually I will also post the annotated slides on the website. But sometimes I make a mistake and then I lose the annotations and then you don't get it. In fact, if you go to the course website and you look for the lectures, you also see the lectures for last semester. And you see the annotations there a little bit different, but so there you can. I will do the same again here, but don't count on it. Occasionally it doesn't work out. Okay. So, wow, you know what? It's 10 o'clock.